I think we can officially start. Welcome back, everyone. So we're nearly done with the first week of calculus. Any questions or comments with what we've been doing so far? Okay, well, one way to think about the content we've gone through is 2.1 is just motivation. It's the section you ought to talk about so that we know we have a purpose when we're doing all this work on limits. Limits were introduced in section 2.2, the definition, but we're mainly playing around with graphs to see what happens with limits and how to visualize the definition of what happens when we take one. And finally, 2.3, which we're about to start. Now we're going to calculate limits analytically using nothing but the limit laws. So our full assignment number 1 is on the table. All sections are filled out. And for some of these sections, sometimes the problem is just a single one. That might mean it's slightly longer. If it is a longer problem, I'll change the point value on it. All these problems by default are worth 5 points, but this one says problem number 5 and 8 are 10 points each. So those ones are slightly longer right there. So I try to give you a guidance on what level of point values you can expect on a problem to problem. And certain problems have extra things expected that I just wanted you to be aware of for the sake of grading. So I'll come back to this comment here as soon as we get to it on our coming problems. Well, any questions at all, folks, about the homework? Okay, and just as a reminder, we showed this last class, but to remind, if you're working out, say, a different edition of the book, click on assignment number 1, and it's going to list out the actual exercises and the associated back of the book solutions to those exercises. I'll get in the habit of doing that for each of the assignments. Okay, well, I guess we're ready to start. Now, the limit laws, it's a long list of different things that you're allowed to do algebraically as you calculate a limit. If we open them up right now, this is what it looks like. And we're going to be using essentially all of these today. Our goal is just to become familiar and know what things can we take for granted when we go to calculate limits, what procedures are allowed, what procedures are not allowed. And I mentioned there is one analogy to this, exponent laws, strangely enough. When you're first learning exponents, here's our analogy, it feels like we're just being really, really cruel and terrible to people because that is a lot of formulas. These are the limit laws, or excuse me, the exponent laws that we really take for granted on a day-by-day basis. Some of these we'll be using and they can get tricky here and there. And that's essentially what we're doing over here. We're exchanging all those properties of exponents for different types of properties for now limits. And by the way, just for fun, if you want any review on exponents, here's a worksheet here as well. Well, I think we're ready to finally dive in. The major thing about these limit laws are this statement right here that we mentioned. There's 2 functions that are being discussed on all these limit law properties, but the underlying assumption is that the limit of f of x and the limit of g of x as x tends towards a, they both have to exist, meaning they come out as a finite number, no infinities, positive or negative. If those limits exist, now you have these wonderful kinds of properties. And you can imagine why this is so important for the limit to exist. Say, for example, if this one failed, then there's no meaning in limit law property 2 because that would fail right there as well. The whole thing would be an undefined if one part doesn't exist. The rest is ruined. So if we look through these, they're saying some things that are kind of nice for us. The limit of a function plus another function is just the sum of the limits of the individual functions. Same if we take a difference. If we multiply by a scalar, well, the good news is the scalar can come out and we just take the limit. After we do that, multiply the result by the scalar and so on. So instead of going through these line by line, my thought is we'll be practicing these as we do this document. And I'll pull up this, maybe put it over here, and just highlight which one we're using as we go. Does that sound all right to folks? Okay, so these notes will stay up top, and this is just kind of the co-pilot to that. As long as I can navigate my windows well, there we go. Okay, so let's start off right here. This example number 1 is strange. I have 2 functions. Here's a f of x, a g of x. I lied, there's 3 functions. There's also an h of x. I don't have the graphs. I don't even know their definitions. But what we do know is they have three different limits that are satisfied. As x tends to 2 in the limit of f of x, we get 4, and so on for g of x and h of x. So the whole purpose of this example is, again, just practice with these limit laws right here. And make that a little bit smaller, that will help. So let's start off with, say, this one right here. If we were to take a limit like this one, well, I don't know what happens to f plus 3 times g of x. We only know what happens to the limit of f of x alone. However, if you see a plus right here, we hope, our hope of hopes is that there's some kind of distributive law. It turns out for limits, there really is. We can say that this is equal to the limit as x tends towards 2 of f of x plus the limit as x tends towards 2 of this function, 3 times g of x. I'll put 3g of x here. And now we can go from that stage. What we've effectively used is just limit law number 1. The limit operator essentially distributes across. And we could have saved some extra steps because we know the limit as x tends to 2 of f of x, that's just a 4. So our work is done there. But I don't know this limit necessarily, right? We just know that g of x goes to -2, and this is 3 times g of x. So our intuition might be this whole thing should just be -6. But the justification is really right here. There's a constant, say lowercase c is playing the role of 3 for us, multiplying a function. That constant can commute outside the limit operator and end up right here. Let's take that additional step on this one and then solve the whole problem. Any questions first? Okay, I'm going to close that one down, and I guess colors are going to help for this. The limit of f of x is 4. So this whole thing just converts over to a 4. Then plus, I'm going to take one step to move that around just to illustrate the limit process. 3 times the limit as x tends to 2 of g of x. Now that we have this one, we know that value is going to come out to -2. We're essentially done. This is now 4 plus 3 times the limit of g of x. So this portion here becomes a -2. Now it's just a arithmetic order of operations problem. We'll have 4 minus 6. And so the entire value comes out as a -2. Well, we did it, folks. That's our first one down. I'll put a check here just to remind myself we solved that one. Any questions at all getting through that there? Okay. The next one's a little bit different because I have functions f, g, and h. But this one has something extra. It has x squared thrown in there. It's just another function, a fourth one. And so when we go through this particular problem, let me put it just below here. Well, oh, there's also a square root. Somehow my eyes did not read that the first time. So it looks like we need a lot of limit laws on this. And just so we don't have to scroll too much, I'm going to temporarily paste this down below for easier reference. Okay, so as we go to do this one, first let's open up our limit laws. And anyone see a limit law so far on this list that looks like it could be helpful out of 1 through 5? I agree with 4, absolutely. It takes a little bit of time to train our eyes to know how does 4 work for us. But on this one, think of the f of x as being x squared. That's one function. Think of the g of x as being this root of the f function as well. It's 2 different functions. And if you're taking the limit of a product of functions, then just take the individual limits and multiply them together. So I don't know what happens to x squared root of f of x, but if we break this apart, we'll be able to get down to the individual given limits below here. So here's our first step. This is equal to the limit as x tends towards 2 of x squared. Then we'll multiply that by limit as x tends towards 2 of the square root of f of x. Lots of ofs there. Well, it looks like we made the problem worse, but I assure you this is a little bit better. We just have to find the right limit law to combine everything with. First, we look at this right here, limit as x tends towards 2 of x squared. This one is not as bad as it looks. Anyone happen to know the answer to that one? It is 4, absolutely. What happens with this is, well, if you imagine what the graph of a parabola should be, a quadratic, it looks like this. There's no holes on that graph. It's continuous everywhere. And so if you get closer and closer to 2, well, the output to the squaring graph, y equals x squared, ought to get closer and closer to 4 altogether. So that's essentially what's happening on that limit. But this could make you kind of squeamish depending on how much you like or hate graphs, right? The good news is it's also in the limit laws. Let's go and find it. Somewhere here is the limit law I want. Somewhere. Here it is. This limit law right here is probably the most powerful limit law. It's going to turn into an entire section on continuity down the line. It says if f is a polynomial or a rational function, and we're in the domain, good news, the domain of a polynomial is all real numbers always, then the limit as x tends towards a is f of a. That's what we're going to be using. And effectively what happens is, here's our f of x. The a that's getting plugged in is the 2. This just becomes 2 squared. So that's direct substitution in action for us. Any questions about that before we go to evaluate it? Okay, let's show the step on this one, and then we have to untangle a bit of a mess over here, but we're getting there. I'm going to move my equality symbol. I kind of painted myself into the corner with that graph. This now turns into, here's the squaring function, and the input of 2 just goes right inside by the direct substitution property. Now it'll be multiplied by this other limit. I guess I'll keep parentheses on it. Limit as x tends to 2 of square root f of x. Well, if we look at that square root function, there's a limit property about that as well. There's something about an nth root. I think we have, yeah, just the nth root right here. There's no n there, but the index is assumed to be 2. So there really is by convention. So we're using this property with the index of 2. And it says the limit operator can commute inside the square rooting function. This is another matter on continuity we're going to see later. So this limit as x goes to 2, it just pops right inside the square root function. Again, it's not that we're trying to memorize all these verbatim. We just need to know what's allowed. And once you get a feel for it, it's really kind of like doing exponents. You crank out an exponent, you don't necessarily think, what exponent law was that? You just become familiar with what's allowed and what's not allowed. So going back to this one, it'll turn into the square root of the limit of, as x tends to 2, f of x. But now we're in business because we know that limit. Oh, that's the wrong color. Let me fix that. We know that limit to be exactly 4. So this stage is done. 2 squared comes out as 4. Just to show the steps, this turns into the square root of 4. And so the whole thing comes out as an 8 altogether in the limit. Any questions on getting through this one here? This right here? Oh, it was from taking that limit right there that was given at the top of the problem. Other questions so far? Okay. Well, there's one last one, and we still haven't done h of x, so how about one more? Our h of x problem came from this one. Let me just put a check here to remind me we've taken care of all of these now. And this one, we're dealing with a quotient. You probably already might suspect something could go awry here. If you have a quotient, a division of functions, and you're taking the limit of it, any volunteers for what would be maybe like a worst case scenario on this limit? Kind of the hint on this one is even if we have all these wonderful limit laws supporting us, we still have to avoid certain issues, like division by zero could suddenly just break everything. We could never escape that. And so if we're looking at the limit as x tends towards 2, we're probably concerned now, right? H goes to 0 in the limit as x tends towards 2, and h is also in the denominator here. Well, let's take a look at the limit laws to see just what we can get away with on this one. Because we see a fraction, we're probably going to be near the top of the list and use property number 5. Now, property number 5 says you can take the limit of the numerator, just plug in the number, divide by the limit of the denominator, if the denominator doesn't turn out to be 0 in the limit. So this is a really big provision. Our denominator did turn out to be 0. So this is a case where we just say does not exist. If I look at the instructions, it's told us to briefly explain why if something doesn't exist. And it really can be pretty brief. Oh, I didn't say the word brief there, but it is allowed to be brief. You can just simply say, since the limit as x tends towards 2 of h of x is 0. You could also say, and h of x is in the denominator, but it would be okay if you left it right there. I'll assume you mentioned that because of h being in the denominator. So it's only because that went to 0 that means the whole thing just doesn't exist. Well, any questions at all, folks, on running through these so far? Okay, again, our whole goal with this is just become familiar with these limit laws. This is more of a warm-up kind of exercise because we had very, very limited information about all three of these functions. We just knew a limit they take when x tends towards 2. So let's take maybe a bigger limit where we have a real function to work with. And that will be this example too. Now, I want to take a lot of steps with this example, and I'm never going to duplicate these instructions. So when you go to do this in homework, you don't have to take as many steps as I do, and certainly never on an exam. The exams are timed, so you don't want to take unnecessary steps if you can avoid them. So the reason we're doing these instructions, the only reason is we're just trying to get familiar with limit laws down below. So think of this as kind of an unusual exercise. On each step, I'm going to try to give a justification of which limit law I'm using. Now, looking at that function, if it looked like this, I'm going to correct it in just a moment. So please don't copy this just yet. It's not quite what we want to do. But if you see a function like that, that's really great news for us. You can pull up the limit laws, come down right here to direct substitution. That becomes a polynomial. All a polynomial is a rational function. And a rational function is just a polynomial divided by some other polynomial. That means this problem would satisfy the direct substitution property. All you're doing is putting a 2 here, a 2 there, and simplifying as you go. A really wonderful problem. However, if it looks like this, the square root prevents it from being a rational function any longer. It's not a polynomial in the denominator now. So that means we have a couple more steps to go, but it really won't be too bad. In fact, you might ask yourself, did we just do direct substitution at the very end? And the answer would be actually yes. That's why we have a whole new section on continuity. But let's start off with what we see here. There's a ratio of functions, right? So we can begin with limit law 5. We're going to split up the limit, distribute it to numerator and denominator right away. And I'll abbreviate this by saying LL for limit law and 5. Should probably define anything I put in there. L dot L means limit law, meaning that we're just referring to this table right here again. So limit law 5 says that it will be equal to a bigger fraction, the limit as x tends towards 2 of 2x plus 1, 2x plus 8, divide by the limit as x tends towards 2 of the root of 4x plus 1. So limit law 5 takes us to here. It got worse before it got better, but that's okay. Any questions at all, folks, to that stage? Okay, now doing this again, the numerator, we can use a direct substitution on. Let's pull up this and justify why. On the direct substitution property, this up above is a degree 1 polynomial. It means if you're taking the limit as x tends towards 2, you just plug 2 inside that polynomial. So that 2 just literally goes right there. The numerator is essentially done by limit law 14. So I'll write equals LL 14. I'm going to do just one limit law at a time so it doesn't get too busy here as we describe what law we used. The denominator is now lim x tends towards 2 of root 4x plus 1. And now the numerator becomes 2 times a 2 going in here from the limit and then plus 8. So it's getting better as we go. Now we have to sort out what we need to get through in the denominator. Any questions so far? Yeah, go ahead. Up above right here, then you would just get a result of 8 instead. You would have to have a 0 on this and a 0 on that, and you would be okay. You'd get something like 8 over 1, so a limit of 8 in that case. If this was a 0 right here and a 0 right here, the underlying limit would actually come out like this. It would come out as an 8 altogether. So that would be the limit in that case. Does that make sense why? Well, if you put say a 0 right here, all you got is the 8 in the numerator. A 0 would have to go there as well, and so you'd be left with a root 1 in your denominator altogether. Does that help with seeing it that way? Gotcha. So if we had a 0, we'd be okay. The only trouble is if we got a 0 in the denominator, like say, what happened on this one? This was a big problem because h went to 0 on the limit itself. Is that what you were asking about? Gotcha. Other questions at the moment?
Why would you be able to directly substitute 0?
Oh, it would have to be like a whole different question. This would have to be lim x goes to 0 instead. It would be okay because we'd still be taking a square root of a positive number. If it converted to negative in there because we chose 0, then we would have had a problem. Well, we possibly could. Eventually, that's the direction we're going. But on this problem, we're showing each step by the limit laws just to track what are the limit laws saying to justify eventually just plug 2 into everywhere. So it's more about just going through this stuff right here. And when we go to the next examples, we're going to do them a little bit more directly. I haven't written them down since we'll see which ones we ought to solve. This will be pretty much our last problem of the day. Does that make sense so far with those questions? Gotcha. Question up here? Sorry, I didn't quite hear you. Yeah, exactly. It has to be either rational or a polynomial, exactly. So that's why we have that extra step because of the square root. If that square root was gone, we could have just plugged the 2 everywhere right away. We'll eventually be able to do that, but none of these properties really signify how. We need the extra section coming up on continuity, 2.5. But other questions so far? Okay, well, let's see where we are on this one so far. So our numerator, it's just going to work out to a glorified 12 altogether. But now in the denominator, we need to force the limit inside that square root. But we've done that once already. Let's look up that limit law. Let's see here. It was limit law number 11. The law says your limit can commute inside the root of any index. But if n is even, this is another issue we have to worry about. The limit should be positive or else we're getting a complex value number. And since this is only real value calculus, we're avoiding those kind of topics. So on this one right here, we can, oh, I forgot the limit law. I think it was 11. Yes, by limit law 11, we can say that this is the root of limit x tends towards 2 of 4x plus 1. But now at this stage, we're pretty much done. Right down here, this is going to be limit law 14 once again, using direct substitution, because 4x plus 1 is now a polynomial. We're just taking the square root of that result right there. So one more step and we'll be in business. Let's look that up just to make sure we have the right accounting for that. Yes, we're dealing with the limit of a polynomial. Then order of operations says we're not worried about the square root until after. All we're going to do is plug 2 right inside of that 4x by limit law 14. So limit law 14 now says this 2 goes right here. So we'll have 12 divided by the root of 4 multiplying the 2 plus 1. This stage, we still have to simplify the answer, get a value out. We'll have 12 divided by the root of 9, which means we have 12 thirds. And 12 thirds is definitely 4, so that's probably the better answer on this. Well, we did it, folks. That's running through this whole thing using the limit laws. Any questions or comments so far? Okay, well, what our limit laws give us is once again, a lot of excellent properties that we can use to evaluate limits as fast as possible. The most powerful one is saved for last, the direct substitution property. And because it's so powerful, let's copy it in. We're going to cite this a couple times as we go and solve some more limits. Question first over here.
Numbers like just as this course or like in actual math?
Oh, just this course. Yeah, just our particular textbook. I would say that if you're thinking of just calculus as a general subject, irrespective of a university, if you say limit laws, people are probably thinking of this, but the list might have different numbers of stuff on it. Other questions so far? Okay, so that takes us finally to our big exercise here on example 3. Sometimes I leave my examples blank because it gives us some flexibility depending on the questions asked, amount of time left in class. And my goal is to kind of end on this example 3, since doing everything through the limit laws can be a bit of tricky math we have to get used to. Also in my notes, occasionally, if there's just extra time, I like to throw in some additional stuff. This is the squeeze theorem. I didn't assign any homework problems about the squeeze theorem, but if we have time, this would be one such problem. We may not be able to solve every application. We have to get to the important stuff on the homework and on exams first. If you're curious about these, we can make an effort. If we can't finish it in class, you're always welcome to email me, and I'm very happy to run through the solution and just post it onto Moodle. So sometimes there's a little bit extra. This application is purely a mathematical one, but as we get further, the applications will come from things like the biological science, physics, chemistry, and so on. So it'll get more interesting as we go. But now for the moment, let's start taking some more interesting limits. This function is, let's call this part A. I'll have the question in black, and as we go to solve it, I'll move over to the other colors, probably blue or green. So we want to take the limit as x approaches 3. Let me read that carefully. X approaches -3 of this function, x plus 3 divided by x squared plus 4x plus 3. So that's our limit we'd like to take. And when you see this function, that's kind of exciting in a certain sense, because this is a specific kind of function. Anyone happen to know what type of function it is? The hint on this one is, you see a fraction bar, and there's no weird things like square roots or exponents of like pi or 3.2. Well, it's a ratio of 2 polynomials. It's a rational function. And rational functions are great because, oh, I thought I was going to paste something in. We have the direct substitution property at our beck and call. But the direct substitution property does have one problem if you're dealing with rational functions. It says A is in the domain of your rational function. Well, rational functions have excluded values that are not in the domain, so we may well have an issue with this one. If you plug -3 into this entire thing, I'll just write this out as scratch work. We'll get 9 minus 12 plus 3. That's 0. So that tells us -3 is not in the domain of this rational function. This is like the worst case limit to even calculate for this function right here. Doesn't mean it doesn't exist. This truly actually has a limit. We just have to do something to find it. Anyone happen to know what this something might be? Absolutely. If we factor out that bottom, we can now start to simplify this function and change it. But here's what we're effectively going to do. Let's pause right here on this thought of changing the function. And let's go back to section 2.2 for just a moment. What we're really doing is this. If we were to try to take this limit as x tends towards 1 of this function, you would need to factor it and simplify it. Even though we're going to say it's equal in terms of limits, we still have a problem because changing the function is changing the nature of the graph, the underlying function itself. But as we simplify, those two functions are going to be equal except for whatever the excluded values are. And it just so happens the value of the limit does not care about one single value. We're able to just completely sidestep that entire issue. Does that make sense to folks so far? Okay, so our work algebraically is essentially taking this graph and plugging in the hole so we can eventually use direct substitution. We can't on the original function. We have something undefined to begin with. So this is what it looks like when it all comes together. Like you said, we're just simply going to factor this. Let me delete this scratch work for the moment. And now we can say that this is equal to the limit as x approaches -3 of x plus 3 divided by, factoring the denominator, probably a likely yes before you even start factoring is, only way this simplifies is if x plus 3 is part of that factorization. So that's not a terrible guess to begin with. We need to come out with x squared plus 4x plus 3. So x plus 1 would in fact do the job. So we have a factorization, which is going to allow for this cancellation. And now it's equal to the limit as x tends towards -3 of 1 divided by x plus 1. We change the function, which is what's right here. It's not the same as this one in black, but it agrees everywhere except that one excluded value, -3. So like we were looking at the graphs before, we plugged a hole, and this function right here will satisfy, oh, that doesn't work. Let me try again. It will satisfy direct substitution because -3 is in the domain of this brand new function. Plug it in right here, and our work is done. So that's what we're going for on these kinds of problems. It's all about trying to find a way to use direct substitution. Any questions so far? It'd be kind of like this graph right here, essentially. Or the function on the right here. This one right here? Yeah, this function, the 1 over x plus 1, the simplified version, is now similar to this situation right here. Or I should circle right here. So we took something like this, which is a convoluted mess. +1 is not even the domain. Simplify to x plus 1, giving us that function. And now we're going to get the correct limit of 2 altogether. Exactly, yeah. In our case, I believe it was -3.
Okay.
It's just the nature of limits does not mind if something happens at the value we're going towards. Exactly, yes. We're going to the same value on either end. Does that make sense so far? Gotcha. Other questions at the moment? Okay, So for this particular limit law or limit, we're essentially done. I'll put here a note. I may not say this every time, but this is now by direct substitution. We take the -3 and just simply plug it in right there. So now we have 1 over -3 plus 1, which is -1/2 for the limit. So we did it, folks. That's our first nasty looking limit. This says the rational function, although it's undefined at -3, the closer you get to -3, the closer the graph height is going to get to -1/2. Any questions at all with that full run through? Okay, suppose you did do this as a homework problem and it's an even number problem, so you don't have the solution from the back of the book. Or maybe it is an odd one and you just want to check it out. One thing you always can do is grab your favorite graphing calculator. Mine would be Desmos only because I'm in class. It's just an easy one to bring to class. Now let's see if this really works out, if it passes the smell test. All you have to do is plot the function, and you could do it like this. F of x equals, we don't care about the returns of service, we'll put that away. X plus 3 division x squared plus 4x plus 3. I'm going to put it in domain because we only care about nearby -3. So I'll go -4 less x less -2. So if we're close to -3, we should be close to -1/2 at the height of that graph. Let's blow it up and see. Right around -3, notice if I stop right here, it's truly undefined right there at -3. I wish that technology would put an open circle right there just to convey there's something undefined. But the way they plot, they're connecting the dots. If I lift the mouse, it shows the connected dots. So that graph is a little bit misleading when you take a look at it. But take a look as we get close to -3 from the left. That's close to -0.5, and I can make that closer if I zoom in more. If I'm to the right, I'm also close to -0.5. And this is the numerical evidence that we are probably correct right here. It's not a proof or a guarantee, but it gives us evidence that we are in the right ballpark by saying -1/2. Well, any questions so far, folks, on getting through that one? Okay, what's pretty much happening on these limit problems is it's like a tour of algebra you've seen before. We factored something out of nowhere, and for the next one, it'll be a brand new algebraic issue. So let's try a slightly harder one next. I'll put a boundary here so the problems just don't conflict, make it a little bit more readable. And all the parts on this are the same. Here is part B. Oh, and I do want to say one extra small thing. There's also this comment to use correct limit notation for full credit, the same comment we mentioned on the exercises. And using correct limit notation means we're copying these as we go. It is kind of tedious, but there is an extremely important reason for that. So let me put down a really quick blurb right here for the reason of correct limit notation, since it's important to the homework, and then we'll go on to the next one. So the reason this is emphasized, and it's not worth a lot. If you did everything but didn't copy those limit statements, you might lose a point out of a 5-point problem, and that's not really a huge deal. But the reason it has importance is because 1 over x plus 1 is not -1/2. Definitely not. It only takes on that value if you plug in the right thing right here. The correct statement is that 1 over x plus 1 equals -1/2 only in the limit as x tends towards -3. This is the ingredient that we need to put in here to make that equality precise. And in math, we just have to say what we mean and mean what we say. And that's the purpose of the correct limit notation right here. Does that make sense to folks on that small issue about notation? Okay. And again, if you forget it, it's not the hugest deal. You might lose a point on your paper. If you forgot it on every single problem, I'm only really going to take off 1 point and give you a reminder. I'm not going to try to nickel and dime you on your entire homework assignment, but it's something important enough to be mindful of. And it's something, especially if you're taking more calculus classes, that could cause harm if we weren't careful enough about. So let's now try our brand new problem here. Yeah, go ahead.
So what if I'm working through problems? I keep stating the limit as I go through it, but the very end blocks in the very last, number answer to it. Is that okay, or do I restate the full answer, full credit?
I think you're okay. You mean like if I did say
Yes,
this?
you did that, exactly.
Absolutely. The way I'm trying to present the answers are the way I would probably expect them from the homework as well. So if you stop like that, I'm absolutely happy with it. I think boxes are great because it definitely directs both me and you of where the answer is at. But if you write it this way, if you are able to track the equalities, I'm not as worried about the boxes. It's more of a personal preference at that point. Other questions so far? Okay, thanks for asking about that. Now let's try off this new limit. Again, each limit we do has a brand new algebraic issue we need to navigate. And I think, let's try this one out. Will be a limit as a variable x goes to 0. We'll have a fraction with the numerator being square root 1 plus x, then minus 1 outside the root, all of which is divided by just x. So that's our function we'd like to work on. This one's not a rational function because of the square roots right here. Take that off and yeah, it would be rational, but it would also simplify a whole heck of a lot. And if we even try to use direct substitution, which we really can't as it stands, it's not a polynomial rational, but if you tried, you can't plug x equals 0 there. You've immediately divided by 0 right at that stage. So we have to do something to this. We need to have a cancellation happen like we see here, so that we can eventually use direct substitution. This one is really weird. I would probably never guess this. Anyone happen to know what we need to do algebraically? Sorry, say again. We can't necessarily square it because we have to leave the value of here just as it stands. If it was something like this, if there's an equality and we had maybe some other function here, we could have the potential to square both sides of the equation in that case. But as it stands, we cannot necessarily square this function right here. Yeah, go ahead. But if we did try that route, that is a great thought because now we're using limit laws in that case, but we would still have a 0 in the denominator on the very last step. Once that limit is attached right here, that's when we have that division by 0 problem. That's always a nuisance, isn't it? Other suggestions or thoughts so far? Yeah, go ahead.
I don't know. I guess we could do square root of 1 plus x plus 1 over square root of 1 plus x plus 1.
Absolutely. That's the magic ingredient to this whole thing. We need a conjugate. And I like this problem because it'll happen in the homework as well. So let me put down a really fast formula. And if you see a square root, there's 2 terms, that might be an indication a conjugate might work. First, here's the formula that's related to all this. If you have, let me try to put it right here. If you have a plus b and take a minus b, sometimes these are referred to as conjugate pairs. They're essentially the same except for the sign in the middle is different. If you expand this out, you get a squared minus b squared. That's kind of the spirit what you were asking about. We need to somehow square this to remove the square root. That's what's going to make it happen. So now with the conjugate, we'll go, let me make one extra step. I want black to be where we started. And then when I go to blue or green or something else, that's when the solution is appearing. That way, if you come back here, it won't look too crazy when you go to read this. So I'll say equals, limit as x goes to 0, root 1 plus x minus 1 over x. And here is that conjugate. We multiply by root 1 plus x plus 1 over root 1 plus x plus 1. In green, that's just the glorified number 1. So we're not changing anything about the limit. Multiplication by 1 is innocuous. Let me just say that this is the conjugate. But now when we go to actually expand all this out, which we have to, we're going to FOIL across the numerator. And I'll leave this at brackets right here. I don't want to distribute the x in because our actual goal is to cancel x. So we can set x to 0 and not worry about that factor right there. So if I multiply, say, here to here, that's just the a squared portion. We're going to get root 1 plus x times root 1 plus x, but that just solidifies into limit as x goes to 0 of just 1 plus x. Completely wipes off the square root. Now notice there's only 2 terms here, and that's because when you multiply to this, I have positive root 1 plus x. Multiply here, that's negative root 1 plus x. They're just gone. There's almost no reason to copy them down, unless it's just for emphasis. Not a bad strategy, actually. But we can now go to really just this portion. It goes a squared minus b squared, and the minus b squared comes from here to here. It just becomes negative 1 times positive 1, so minus 1. So that's all that happens in the numerator once we FOIL. And it's a fast process because of that conjugate pair formula right there. Probably my favorite factoring formula ever. It does come up a lot even in this class. Well, any questions on getting through that portion? Okay, so we FOIL across the numerator, but in the denominator, I'm going to do something slightly different. I'm going to just leave this x alone, keep these brackets, and not distribute inside. So root 1 plus x plus 1, and then close bracket. Again, the reason for that is, even at this stage, you still cannot use direct substitution. If you plug x is 0 right there, then we divide by 0 again, and everything is for naught, right? But when we multiply by the conjugate, we got that cancellation. Positive 1 cancels with negative 1. Now you can cancel the factor x over x at the same exact time. That x is canceled, that x is canceled. All that's left in the numerator is 1. Let me recopy it so it's not so busy. We have limit as x tends towards 0 of 1 divided by root 1 plus x plus 1. So now that's our entire limit. Well, looking at this, it's still not a rational function, but let's take a look at what the limit laws say. That's not it. Let me try again. There we go. The limit laws say if you're going to do this limit, you can first invoke limit property 5. Take the limit of the numerator, divide by the limit of the denominator. Well, what would be the limit as x tends to 0 of 1? That's taking the limit of a constant. And is that somewhere there? Yes, it is. Property 7. If you're taking the limit of just 1 as x tends towards 0, nothing happens. You just get 1 right back. That's limit law property 7, so the numerator just stays right the same. The limit law would go to the denominator, but then we can force it inside the square root. We've done it twice already. And then 1 plus x, that is a polynomial. We can use direct substitution on it. We won't always take every single one of those steps. We did that earlier only just to justify where the law was and how to use it. Instead, this is what I would do. It's equal to 1 over root 1 plus, and let me give this a special color, 0. This is now by a direct substitution, not the kind that we see yet in the notes, but we'll see it very shortly on continuity. And that's our result. We still need to simplify it. Right here is the root of 1 coming out as 1. So the whole thing settles to 1/2 exactly. And if you want extra numerical evidence, say it's a homework problem, you could plot the thing and see if it really is getting closer to 1/2 as x gets close to 0. So the major trick on this one was conjugate. Yeah.
So what would happen if you were
Sorry, what did you mean? Say replace the root right here with?
Yeah, there's places for really like say power to.
Oh, gotcha. Power two right here. You know, we may have to do something different on this one. Absolutely. Tending towards zero here, we may just have a result of something like this. It's just positive infinity this time. We'd possibly have to consider graphs, seeing what's happening, but there's no cancellation in that new problem. That's going to eliminate the x in the denominator. So yes, we would need different techniques, probably a graphical analysis in that kind of case. This problem was just rigged to work out spectacularly if you have a conjugate and fall on its face otherwise. Other questions so far about that? Okay, so far the theme has been factoring is absolutely going to be useful. That's what we did right here. Let's mention that. This is a reminder of that's an expectation on the homework. Then we had to use a conjugate, and there's still other algebraic issues we need to worry about. So let's try an even new one. This one is something that people are familiar with. It's just a little bit tedious. It's good to practice if you're feeling a little bit rusty on this kind of math. I'll call this part C, and just to make sure nothing kind of gets mixed up, let's put a border there. And this time, let's take the limit. Let's get a good one too. As we get really used to x's, so sometimes it's good to mix it up. Let's take the limit as t goes to 0. T might mean time if it was an applied problem. And we'll have 1 over t minus 1 over t squared plus t. So that's our new weird situation we need to resolve to get a limit at. Now, direct substitution will fail on this one because although 1 over t is rational, you can't put 0 there. We can't put 0 in those ones either. So once again, we're just dealing with a weird case. Anyone see what the solution might be to make this limit work? It's kind of ugly work algebraically, but the hint is if you see two fractions and you can't do anything with direct substitution, try adding the fractions together. Sometimes when you do that, things cancel out just right. If I can get rid of these factors of t that are stopping us, we might be able to make this work. So here's the idea. We must add the fractions. But that's also a little bit annoying because fraction addition in this context also comes together with factoring. You never want to add fractions together unless denominators are fully factored, or you could be accidentally doing a tremendous amount of extra work. So I'm going to start by factoring out the greatest common factor in that denominator. Then we'll combine the fractions together. So this is what it would look like if I was working this out. Lim t goes to 0. The parentheses are just saying everything inside there is affected by the limit. I'm going to make a fraction with an extra long fraction bar, 1 over t. Minus, let's do it again, 1 over a little bit longer than before. Now we'll factor this one by just taking out the greatest common factor of t. It'll be t times t plus 1. And let's go for a different color here. Now that we got to that stage, we usually look at the bigger denominator. That's probably going to be the least common denominator for us. Definitely in this case. Go to the other fraction and just throw in what's missing. What would you say is missing from that denominator by the red dot? Absolutely, so we just throw it right in. But to make this work out algebraically, you must do above as below, much like the conjugate trick. Now we're in business. We have the least common denominator. We can subtract across the numerator and maintain the least common denominator. That look all right to folks so far? Awesome. For me, these are one of those kinds of things where, again, if I haven't done this in like, say, 5 years and I have to suddenly do it, well, it's not comfortable, but it comes back as you just delve in. If you have any questions about this kind of stuff, never hesitate to ask. I'll always be available to help out. So on the next step, limit as t goes to 0. Here, we're just making one fraction, so we don't even need parentheses anymore. The parentheses was because there's two terms the limit was affecting. Least common denominator is t times t plus 1. That multiplication by 1 can be dropped, so we'll have t plus 1 minus 1. And notice this is starting to clean up for us. We have like terms that cancel, so they're gone. I'll take one additional step so I don't have a bunch of chicken scratches on one tiny step right here, but you can do all your cancellations if you prefer. So limit as t goes to 0, now it's t divided by t plus 1. And I forgot to copy something. Let me try with my denominator again. T times t plus 1. Here's the next cancellation here and here, leaving a 1 in the numerator. Now next, we have limit as t goes to 0 of 1 over t plus 1. That's a much better function. It's completely different than this one. Well, not completely, they differ at one point. That's when t goes to 0, and they're going to agree everywhere else through our simplification. But the even better news is, if you send t to 0 right here, it's allowed, that's a rational function, and we are not dividing by 0 any longer. We just get 1 over 0 plus 1. Yellow to show how the direct substitution occurred. And so the limiting value on this strange looking problem turns out to be exactly 1. We did it, folks. This one's kind of nasty because it was more grungy looking algebra we had to climb through, but it occasionally does happen in this course. Any other questions so far, folks, on getting through this? Okay, it looks like we have a little bit more time to spare because we have about, let's see, 10 minutes-ish to get through. I'll leave it up to the class. We can do a part D on this, a new function, or we could tackle the application. Any volunteers for one way or another? Part D, that might be a good way to go. Sorry, was I? Gotcha, no worries. If you're curious about it, I can post the solution down below after class so you can see how it goes. But let's give this a try then. Maybe one more for the homework. And on part D, there's not as many tricks to this one. I think I got through all the things that are going to be weird issues on the homework itself. But this one is more kind of where we're going with limits, is the spirit of this problem. This one will be the limit as h goes to 0 of -5 plus h to the power of 2 minus 25, all of which is divided by h. H is kind of a strange variable here, but it does have its purpose. So while you're taking a look at that, let me give you a moment. I want to point to section 2.1 to show you where this limit is coming from, because it definitely looks kind of strange. So in 2.1, essentially what we're doing is this. The h's are coming from this kind of thing. We mentioned we want the slope of the tangent line. The secant line has to adjust. That means h needs to get smaller and smaller. So at this point moves to the left and overlaps. Can never fully overlap, or you've divided by 0 at that case. And certainly that's what we're looking at here. You cannot send h to 0. You're only allowed to approach it in the limit. But there's algebra we can do here. If we expand that numerator, maybe something cancels, and if you cancel out that h, we'll be able to evaluate the limit directly. Any questions before we give this one a try? Okay, so this one is really not too bad. It just looks strange. The variable is h, which is getting smaller and smaller. And the numerator here, if we expand, will be -5 by -5, -5h twice, plus h squared. Then I'll just copy that, -25. All divided by h. Now, what makes this limit work out is anything in the numerator that doesn't have an h must cancel. All the terms that survive do involve h. That means we can cancel even further. I'll take one extra step to show the new cancellations, just so it doesn't get too busy. Now limit h goes to 0 And you can cancel by putting a slash here, here, and making this power 1. That's a really fast way to cancel. I'll do it just by factoring, just to show it a little bit differently. If I factor out an h, this is what it would look like in the numerator. The denominator is just h itself. And so there's that next cancellation. All that survived now is a degree 1 polynomial in the variable h. That means you can now use direct substitution and send h to 0 right here. Now the whole thing becomes -10 plus 0. So the limiting value turns into a -10. So this one's not too bad. It was just a little bit unusual. This one wasn't a conjugate because of the power 2. It was more expand and simplify to get through it. But the context on this one is that value of -10 is much like letting h go to 0 right here and finding the slope m, say 3 or 5 in a different problem. Well, any other questions or comments, folks, so far? Okay, well, I think this is probably a pretty good stopping point for us. If you do have more questions, I'll be very happy to help out. I'll be down here. Otherwise, this will be the scope of the notes here. One thing I do want to mention is when I go to assign the homework problems, I do pay special attention to what was actually assigned. And I make sure on the problems I select to do, I put little stars on them, that we actually get to those. So if you feel like some of the problems seem a little bit strange, look to here for motivation. There may be something familiar. If you're not seeing the connection, definitely email me. I'll always be very happy to help out. Or office hours are always a great option too. Well, have a great week, folks, weekend, and congratulations on getting through week 1. It's always the